everyone, welcome back. I'm Dr. Heath, and today I'm going to be walking you through Chapter 11, Section 2 of our Math 3322 course. So in this section, we are going to be going over curves, polygons, and symmetry. So by the end of this section, you should be able to understand and explain simple, closed, and convex curves, including polygons, so defining and identifying those things, naming and classifying different triangles and quadrilaterals, thinking about hierarchy among selected polygons, and symmetries and their relation to planar figures. All right, so first things first, we can define what a simple curve is. So a simple curve is a curve that does not cross itself. So the starting and stopping points may be the same. So one example of a simple curve could just be something like that. We could also have a simple curve stopping and starting at the same point, but something that is not a simple curve would be something that crosses over itself like that. So this is not a simple curve. A closed curve specifically is a curve that starts and stops at the same point. So here, the first example I drew would not be a closed curve, but the second curve would be a simple closed curve. A polygon is just a simple closed curve with sides that are line segments. So next we can talk about a convex curve. So a curve is convex when we have a simple closed curve with no indentations. The segment connecting any 2 points in the interior of the curve is contained in the interior of the curve. So in contrast to this, we have a concave curve, and that is a simple closed curve that's not convex. So an example of a convex curve would be something like this, and an example of a concave curve would be something like this. So we can see in the simple closed curve, we can connect any 2 points in the interior, and the line segment connecting those 2 points is contained within the entire closed curve. But here we see that that breaks because if I take this point and this point and I create the line segment connecting them, it exits the simple closed curve, and so it is concave. So here's kind of a breakdown of what you might look for. This first curve is simple, but it's not closed, and it's not a polygon, and it's not convex or concave. We have to have a closed curve to talk about convex or concave. The second row, this is a simple curve, but it is not closed, polygon, convex, or concave. Then we have a concave, simple closed curve. So this is closed because we begin and end at the same point, and it's concave because we have segments that would exit our curve if we connected interior points. And then we have a simple closed convex curve with the circle. Now we can take this curve. This is a closed curve, but it's not simple because it overlaps itself. So this point here makes it not simple anymore. On the second row of this table, we have a simple closed curve that is convex, and it is also a polygon because the sides of it are line segments. And this last one is a simple closed polygon because all of the sides are line segments, but it's concave because we will have points that, when connected with a line segment, will leave our figure. Something important to notice about polygons is that, and simple closed curves, is that every simple closed curve separates the plane into 3 disjoint subsets. So we have the interior of the curve, the exterior of the curve, and the curve itself. So in this picture, we can see the interior, the exterior, and the polygon makes up the curve itself. And we also call this the sides of our polygon sides, and the points where those sides intersect vertexes or vertices. We have names for polygons with different numbers of sides or vertices. Triangles are 3-sided, quadrilaterals are 4-sided, 5-sided polygons are called pentagons, 6-sided polygons are called hexagons, and so on. When we get up to a certain point, we typically just call it an n-gon. When we think about polygons, we have interior angles of our polygon. So interior angles are the angles formed by two sides of a polygon with a common vertex. And then we have an exterior angle of a convex polygon, an angle that's formed by a side of a polygon and the extension of a contiguous side of a polygon. Finally, we can talk about the diagonal of a polygon, and that is a line segment that connects non-consecutive vertices of a polygon. So here we can see in this quadrilateral, which is a polygon, A, B, C, D, we have an interior angle, which we would call angle ADC, and we see a diagonal illustrated here. We can also talk about the exterior angle of a polygon, so we would extend one of the sides and then think about the angle that's created on the outside of our polygon. When we are comparing polygons, we can talk about whether or not they're congruent. Now, this comes down to having congruent parts. So congruent parts are defined to be parts with the same size and shape. So two line segments are congruent if a tracing of one line segment can be fitted exactly on top of the other, and two angles are congruent if they have the same measure. So in this picture, we can see that segment AB is congruent to segment CD, and then angle ZYX is congruent to angle RQP because they both measure 108 degrees.